are going to start the new concept how we can design the controller. So we'll be using the kernel formula for pole placement controller design, also the observer design. So here let's assume we have dynamics, let me write, for a sister system. For a sister system, the form, let's assume y to the n. So here basically n the derivative and a n minus 1, y n minus 1 plus y1, sorry, a1 y dot plus a naught y equal to 0. It is, no, it is, there is control also, bu, some control input, and let us define this equation number 1. So this is the CISO system where we are having single input and single output. So here we have the input and we have y is the only state available in the system. Now for the system, if A and B, the system and control matrices are written as A equal to minus a n minus 1 minus a n minus 2 minus a n minus 3 dot 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 minus a1 minus a naught 1 0 0 0 0 0 1 0 0, and the last row 0 0 0 0 and 1. This is the A matrix, and B matrix be 1 0 0 0 0. And let us define this equation number 2. Okay. So where a naught to a n minus 1 are the coefficients of plants characteristic polynomial or characteristic equation. Okay, where we can find characteristic equation Si minus A mod of this equal to 0. Or we can write, instead of 0 we can write, let us write s to the power n a n minus 1 s n minus 1 dot 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 plus a1s plus a naught. And let us define, this is equation number 3. So the coefficient of this characteristic equation are being used for finding the A matrix. Okay. Go to the coefficient of the equation 1, the system equation. And if you can write the matrix A and B for this particular system, then we can say the system is in controller companion form. So then we say that the plant is in controller companion form. if you can do in this structure, if you can find the system matrices in the structure, it will actually helpful for us to designing the control. And if you would like to know more about this, you can find the reference book, Fitland. This is already mentioned in the uh, course handout in the website, Fitland book. You can go to the modern control part. There it is, detailed things are done. Now, as you have done the for state feedback control, the gain matrix for state feedback gain matrix, we have k equal to k1, k2 dot 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 kn, because we are controlling n number of states. The dimension of this equation is n. So now, based on this, uh, control gain matrix, we can find the augmented matrix, which is augmented matrix already have done. Augmented matrix, we can write a CL A minus PQ, right? And if you find the characteristic equation of the augmented system, characteristic equation of augmented matrix AM, we can write SI minus ACL equal to, we can write SI minus A plus PK. And let's define the characteristic equation is found to be Sn plus alpha n minus 1, Sn minus 1 plus alpha n minus 2, Sn minus 2 dot 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 plus A1 is plus, sorry, alpha 1 is plus alpha. Okay, let us define, this is equation by 4. Okay, now also we can write, also this is the characteristic equation, right? This is the characteristic equation, this equation 4. Now A minus BK also we can find in matrix form. So ACL equal to A minus BK. Also we can write down in characteristic in matrix form. This is minus AN minus 1 minus K1 minus AN minus 2 minus K2 dot 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 minus A1 Kn minus 1 and minus A0 minus Kn and 1 0 dot 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 0 0, and this is, we can write here 0 0 0 0. So this is our A minus BK matrix. And if you notice, the closed loop system is also in component form. So this system also in component form, this A minus BK. So let us write this is the equation number 5. Now, if both are in component form, we can compare equation 5 and equation 4, and we can come up the uh, coefficient of the S's. So here what we will do is uh, comparing or we can write from equation 34, the coefficient of flow, sorry, equation of 34 here is some 4. Question 5. The coefficient of closed loop characteristic equation must be equal to equation 4, right? So in this condition, we can write alpha n minus 1 equal to a n minus 1 plus k1, and alpha n minus 2 equal to a n minus 2 plus k2 dot 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 alpha 1 equal to a1 plus kn minus 1 and alpha naught equal to a naught plus kn, right? And from this we can further write ko1 equal to alpha n minus 1 minus a n minus 1, and k2 from this you can write alpha n minus 2 minus a n minus 2 dot 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 a n minus 1 equal to alpha 1 a1 and a n equal to alpha naught minus a naught, right? And if you write in vector form, all these control parameters, we can write k equal to alpha minus a. And let us define this is equation number 6. So here we can write so here alpha equal to alpha n minus 1, alpha n minus 2 dot 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 alpha 1 and can write a equal to a n minus 1, a n minus 2 dot 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 a1 a naught. Okay. Now, if you assume state space representation is not in, okay, these are the condition we are having if the system is in companion form, right? But if it is not, how we can do? Because most of the system will handle not companion form, right? So for that case, we already have done the state transformation. The way basically help us to convert any system into controller companion form. So if the system is not it's not companion controllable controller form, we can use this state transformation. So already you have done how to convert the system into diagonalized form. So here we can write x equal to dg. So x is the state, original state, and z is the another state in another domain, and t actually transform from one domain to another domain. So we get from this the original system is our x dot equal to ax plus bu and y equal to cx. So since we are designing the controller, so here this equation is very important. So from this equation, if you substitute this value in this equation, we get, which already have done in our previous lecture, a dash equal to T inverse AT, from which we can write A equal to Tn Ta dash T inverse, and B dash equal to T inverse B, from which you can write B equal to TB dash. Okay. So now for this transform system, also we can design that controller for regulator. This is a regulator problem. We are assuming x is equal to 0 here. Digit signal, so it is a regulator problem. For regulator control, we can write E equal to minus kx. So in place of k, sorry, in place of x, we can write minus ktg, right? Because our state has been changed to tz, and tz we can write here. Now here we can write since kt is regulator gain matrix, when plant is in controller companion form. So now what I'll do is, if you compare the controller, what you have done here, A, and what you are having here. So if you compare both the stuff, we can write. So let us define this equation number 6. From equations 5 and 6, we can write kt equal to alpha minus A, and from which we can write k equal to alpha minus A T inverse. So here we need to know T inverse, which will transform the plant to a variable form. This is already you know. Now we'll take the contributed test matrix, and using which will come up the final Ackermann formula to find the controller gain of the system. So as you have done the controller test matrix, contributed test matrix, contributing test matrix, we have done already. So we have P equal to B, AB, A square B, A n minus 1 B. And now if you substitute, since we are writing everything in this form here, we have transformed the system into controller component form. So we can write in place of A, we can write this, and in place of B, we can write this part. So here, after writing in this matrix, we can write TBS. And one thing, this is for stuff become A square B dot A n minus B. So, and for AB, you can write T A dash T inverse TB. And for this, you can write TA, TA dash T inverse T A dash, T inverse, and T B dash. And for the last term, we can write the last term we can write dot 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 T A dash, T inverse, N minus 1, T B dash, right? And so here, this will give the identity matrix, here also identity matrix, and here also identity matrix. And similarly for the subsequent terms, so we can write T, if we take T outside, we can write B dash, A dash, B dash, A dash square, B dash, dot dot dot, A dash N minus 1, B dash, and this part we can write as T dash, P dash, because all the terms inside the bracket same as P matrix except the dash. So we can write equal to, this is T dash, sorry, this should be P dash. So we can write T P dash, right? So what is the takeaway from this? We can write P equal to T P dash. Now pre-multiply, we are trying to get the simplified form. Pre-multiply by T inverse on both sides. We are having T inverse P equal to T inverse T P dash. And from this we get T inverse P equal to P dash. And again, if we want to post multiply, by P inverse on both sides, here T inverse P inverse equal to P dash P inverse, and from this we can have P inverse equal to P dash and P inverse. Now also we need to, there's an important note here, P dash is actually upper triangular matrix. So upper triangular matrix means the one of the the elements below the diagonal element, diagonal lines at 0, right? So we can write. So here we can find the P dash matrix. Okay, one thing, whatever things we are doing, we'll have the proper example for the system, very good systematic aircraft or any other system, and how we can do all the steps for as an example, we'll be showing maybe in the next lecture. Maybe you find difficulty in this mathematics, but as you will be solving the problem, it will be easy for you. So P dash obtained as 1 minus A minus N minus 1, N minus 2, A2, A1, 0, 1, minus N minus 1, A minus A3, A2, and we can 0, 0, 0, dot, 0, and 1. So now if you substitute this term T inverse in the our this equation where we have written yeah, in this equation, so in place of T inverse we can write uh, P dash P inverse. So uh, the expression the expression T inverse equal to P dash P inverse substituting in K equal to alpha minus A T inverse and we can write K equal to alpha minus A P dash P inverse. And this is called the Ackermann pole placement formula for finding the controller matrix K. This is called very powerful formula called Ackermann pole placement. Now, if you want to look the same thing for the observer design, how can we? The second part we are going to start here, this course. Second part, how we can find the observer design using Ackermann formula. The pole placement can be carried out in the similar manner of what you have done in the for the pole placement design for the controller. So here, let us write for plant, test equation which you write Si minus A. Already you have found before S to the power n plus An minus 1, Sn minus 1, dot A1 is plus A naught, right? Now, if you see here, we are finding the closed loop characteristic equation right here. And also we are finding the matrix A minus B. Similarly, we can do for the observer because in controller design we are using K, but in the observer design we are using L. If you remember the last lecture, we are designing L for the observer design, the same structure. So here we can write, we can find the observer in matrix L which places observer poles such that observer's characteristic equation is Si minus A naught, the observer matrix, observer system matrix. So we can write S to the power n beta n minus 1 Sn minus 1 plus dot 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 beta 1 is plus beta naught. And the observer gain matrix we can find. So here we are assuming in the control design for pole placement control design, we assume the our matrix, the controller matrix in this form, right? The already have done. And here also we have to assume the observability test matrix. So if you remember, we had so here we have the observability test matrix. I'm not going to detail observability test matrix. We had n equal to C transpose A transpose C transpose A transpose square C transpose something like this, right? So here also we can go the same process what you are doing, we have done for the control design. So finally, we are having the control observer gain matrix L equal to in this structure. The same process you can follow B minus A. E is coming from the system characteristic equation. N dash N inverse transpose. Okay, so here beta equal to beta n minus 1, beta n minus 2, beta 1, beta naught, and this is the transpose. This is transpose, you can assume, and A equal to A n minus 1, n minus 2, dot 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 A1, A naught transpose. And so this is how we can find the observer gain matrix. And so we are not going, I'm not going detail of it. So you can find how it is derived. So let's stop it here. In the next lecture, we'll be taking an example how we can implement whatever the concept we have done here. In this lecture, we'll implement the